Our planet is enveloped by a vast ocean, not of water, but of air. This is our atmosphere, a dynamic fluid that's constantly in motion. We might not see it, but this sea of air is as alive as any ocean, with currents, waves, and even its own version of storms. Understanding how this sea of air behaves is key to understanding our climate. Warm air is less dense than cold air. This difference in density creates pressure gradients, which in turn drive the movement of air. Imagine a hot air balloon. The hot air inside is lighter than the surrounding air, causing it to rise. This is the same principle that drives many of the large-scale atmospheric circulations on Earth. Viscosity also plays a role, though less pronounced than density. This internal friction of the air, how easily it flows, can impact the formation and behavior of weather patterns. Think of honey pouring slowly compared to water. These basic properties of air, density, pressure, and viscosity, are the building blocks for understanding the grand ballet of Earth's atmosphere. High above us, a natural process unfolds that makes our planet habitable. This process, the greenhouse effect, traps heat from the sun and keeps Earth warm enough for life to thrive. It's like a cozy blanket wrapped around our planet. Sunlight, carrying energy, travels through space and reaches Earth. Some of this energy is absorbed by the Earth's surface, warming it up. The warmed Earth then radiates some of this energy back out towards space. However, not all of this heat escapes. Certain gases in our atmosphere, known as greenhouse gases, act like a giant blanket. They trap some of the outgoing heat, preventing it from escaping back into space. The main greenhouse gases are carbon dioxide, methane, and water vapor. Without them, Earth would be a frozen wasteland. Beneath the surface of our planet's vast oceans lies a hidden world of constant motion. Massive currents, like giant conveyor belts, circulate water around the globe, transporting heat and nutrients. These ocean currents play a vital role in regulating Earth's climate. One of the most significant of these currents is the thermohaline circulation, often called the global ocean conveyor belt. This system is driven by differences in water density, influenced by both temperature, thermo, and salinity, haline. As warm, salty water reaches the colder polar regions, it cools down and becomes denser. Eventually, it sinks to the ocean depths and begins a long journey back towards the equator. This continuous cycle acts as a giant heat pump, distributing warmth from the tropics to the poles. Ocean currents also carry nutrients essential for marine life. The atmosphere and the ocean are locked in a perpetual dance, each influencing the other in a delicate balance. This intricate interplay is evident in phenomena like El Niño and La Niña, cyclical climate patterns that arise from the interaction between the Pacific Ocean and the atmosphere above it. Normally, trade winds blow from east to west, piling up warm water in the western Pacific. However, every few years, this rhythm is disrupted. El Niño weakens the trade winds, allowing warm water to slosh back towards the east. La Niña, on the other hand, intensifies the normal rhythm, pushing warm water even farther west. These shifts in the ocean atmosphere dance have far-reaching consequences, altering weather patterns across the globe. El Niño is often associated with increased rainfall and flooding in the eastern Pacific. La Niña can bring drought conditions to the same region. High above the Earth's surface, invisible rivers of wind race around the planet at speeds exceeding 200 miles per hour. These are the jet streams, powerful currents of air that play a critical role in shaping weather patterns and influencing our climate. Imagine these jet streams as giant, meandering rivers flowing high in the atmosphere. The position and strength of jet streams are influenced by the temperature difference between the equator and the poles. This difference in temperature creates a pressure gradient, which drives the jet streams. Jet streams act as boundaries between cold air masses to the north and warm air masses to the south. These fast-flowing rivers of air help to steer weather systems, influencing the track of storms and the distribution of precipitation. In the polar regions of our planet, vast sheets of ice stand as silent sentinels, reflecting sunlight back into space and helping to regulate Earth's temperature. However, these icy giants are under threat from a warming climate, and their melting has profound implications for ocean circulation and climate dynamics. The melting of glaciers and ice sheets adds fresh water to the ocean, particularly in the North Atlantic. This influx of fresh water disrupts the delicate balance of the thermohaline circulation. Adding fresh water to the North Atlantic makes the surface water less dense, making it less likely to sink. This disruption of the thermohaline circulation can have cascading effects on global climate. It can alter heat distribution, influence regional weather patterns, and even impact marine ecosystems. The consequences of these changes are far-reaching and complex. Earth's climate system is a complex web of interconnected processes, each influencing the others in intricate ways. One of the key concepts in understanding climate change is the idea of feedback loops, where a change in one part of the system can trigger a cascade of effects. Imagine a line of dominoes standing upright. When you tip over the first domino, it sets off a chain reaction, causing each subsequent domino to fall. Positive feedback loops amplify the initial change, like a microphone amplifying a sound. For example, as global temperatures rise, ice melts at an accelerated rate. This melting ice exposes darker surfaces, which absorb more sunlight, leading to further warming and more ice melt. Negative feedback loops, on the other hand, work to counteract the initial change, like a thermostat regulating room temperature. For example, as carbon dioxide levels increase, plants grow more vigorously, absorbing more carbon dioxide during photosynthesis. Over warm ocean waters, swirling vortices of wind and rain form, unleashing nature's fury with devastating force. These are hurricanes and cyclones, powerful storms that act as giant engines, transferring heat from the tropics towards the poles. Imagine a hurricane as a massive heat pump, drawing up warm, moist air from the ocean surface. As this air rises and cools, it condenses, releasing vast amounts of heat energy that powers the storm. These powerful storms act as safety valves for the planet, transporting excess heat from the tropics towards higher latitudes. Without these storms, the tropics would become unbearably hot, and the poles would be even colder. However, as our climate changes, these storms are becoming more intense and destructive. Warmer ocean temperatures provide more fuel for these storms, leading to stronger winds, heavier rainfall, and more devastating flooding. In the heart of bustling cities, a phenomenon known as the urban heat island effect is transforming local climates. Concrete jungles, with their vast expanses of pavement and buildings, are trapping heat and creating pockets of significantly warmer temperatures compared to surrounding rural areas. The dark surfaces of roads and buildings absorb sunlight and release it as heat, raising temperatures in the immediate vicinity. This effect is compounded by the lack of vegetation, which naturally cools the air through transpiration. The urban heat island effect can have significant impacts on the health and well-being of city dwellers. Higher temperatures can exacerbate heat-related illnesses, increase energy consumption for cooling, and contribute to poor air quality. In the digital realm, scientists are creating virtual Earth's complex computer simulations that allow us to glimpse into the future of our planet's climate. These climate models, based on the fundamental principles of physics and chemistry, are essential tools for understanding the complexities of climate change. Imagine a climate model as a giant, intricate puzzle, with each piece representing a different aspect of Earth's climate system. Scientists carefully assemble these pieces, incorporating data on atmospheric and oceanic circulation, land surface processes, and the carbon cycle. By running these models forward in time, scientists can explore different scenarios and see how Earth's climate might respond to various factors. While no model is perfect, these simulations provide valuable insights into the potential consequences of our actions and help inform decision-making. For millennia, humans have lived in relative harmony with the natural rhythms of our planet. However, the Industrial Revolution marked a turning point as we began to harness the power of fossil fuels, releasing vast quantities of greenhouse gases into the atmosphere. This human-induced change is now disrupting the delicate balance of Earth's climate system. Imagine Earth's atmosphere as a bathtub, and greenhouse gas emissions as a faucet pouring water into the tub. As we continue to burn fossil fuels, the level of greenhouse gases in the atmosphere continues to rise, trapping more heat and warming the planet. Our impact on the climate system extends beyond greenhouse gas emissions. As we peer into the future, the fate of our blue planet hangs in the balance. The choices we make today will determine the course of Earth's climate for generations to come. Will we continue down a path of unchecked emissions and environmental degradation, or will we chart a new course towards a more sustainable future? The science is clear: climate change is real, it is human-caused, and it is already impacting our planet in profound ways. We are witnessing rising sea levels, more extreme weather events, and shifts in plant and animal life. However, amidst the urgency, there is also hope. By transitioning to clean energy sources, reducing our environmental footprint, and embracing sustainable practices, we can create a future where both humanity and nature can thrive.